Okay, so let me start by just revisiting a little bit the material we discussed yesterday about Make. Do you guys have any questions about this? And I apologize if I look like I'm lost. I'm just looking for all my windows, which are too many. And I want to have the chat window with me. So I think we cover more or less the main things of Make. I apologize again for taking so long, but what I want is to show you a few examples that we didn't have the chance to discuss. They are even after the discussion slide in the set of slides. And these are examples, for instance, which we use a lot also, is an example of a Makefile for compiling LaTeX documents. So if you're familiar with LaTeX, it's a very nice tool for writing papers or thesis or books or whatever. In this case, this is the typical structure that you will find in a Makefile for LaTeX documents. First, you usually put the name. This can be also a command line argument passed to the script or to the Makefile. That's the name of your paper, for instance, manuscript or thesis or whatever. Then target is combined from the manuscript name .pdf. So this is what you want to generate at the end, the target of your compilation in LaTeX. The source file is usually named as manuscript.txt. And then you have a lot of intermediate files that are generated depending on what type of LaTeX compiler you use or IDE. You may get notes.bib or .text backup or a lot of intermediate files that actually you don't want to submit to the journals or you don't want to keep it there. Some of them are needed for linking the document with the bibliography, for instance, or the references, but that's something that you, in principle, don't really need. And so I define all these extensions of the files as chunk, and then I have my funny rule being clean. And then, of course, this is a continuation of the script. Then the dependencies or the rule states that the target in this case, whatever it is manuscript.pdf, depends on the source. And you can put there many other things, like if you have figures that need to be generated or regenerated, or if you have modules or documents that are part of the main document, you can put in there. Usually, if you do LaTeX, you need to do a couple of passages through the compiler and then one through BibTeX. So I have one compilation of the source, one passage for the references of the bibliography, and then a couple more of compilations so that every link is done properly. The all basically depends on the target. That's a funny rule as well. And then the clean rule, what does is looping over all the extensions. That's what you see here for X in whatever is in chunk, all these extensions do, and then remove -v just that it shows what is being removed, and then $sign name and $sign extension. This is not a typo. This is a way to protect whatever is the content of the variable extension. Okay, so it's a very quite simple, straightforward Makefile. I wanted to share it with you. So again, if you're writing LaTeX document, it's a very useful thing to keep in mind. The add is a way to say display this on the screen, or don't display this on the screen, sorry. It's a way to basically remove that. Okay. So any questions about this? Again, it's something that maybe is not directly applied to the course per se, but you will see there are some points of connection with what we will see today later. And yes, that's a really good observation from Francis. Never cut and paste, I would say, code in general from PDF, because usually what happens is there are hidden characters that when you're like, if you're underlining something and then copying and pasting, then they will be carried on and the encoding will be broken. In addition to that, in particular, for the Makefiles, as Francis is emphasizing, remember these things, the tabs that you need at the beginning, they most probably will be converted as spaces. So it's going to be really, really messy. So you will have a lot to fix. And sometimes the messages that you will get are not quite clear of what is going on. Okay. Again, just a simple example. I told you last time that you can run May with --help, and that gives you help about Makefile. But there is something that is really, really nice, and it ties very nicely what we are going to be discussing later, that is ways to document your Makefiles. So for instance, it would be nice if I get a Makefile to have an idea of saying, okay, what targets can I do without needing to go and look into the Makefiles. And again, this is keeping in mind that sometimes Makefiles can be really, really big and complicated and convoluted. So maybe there is a way we can do that, and there is indeed. So one very simple thing that we can do is use a funny rule called help. Basically, help, what we'll do is just list what options, what targets are in the Makefile. So for instance, I could have a Makefile which has a debug option, which will compile the code with debugging flags. I could have a target that is build, and then it will compile the code with the default options. I could have a target which is install, which will install the package, and I can have a target which is clean, as we have seen, that remove the intermediate or auxiliary files that are needed. Okay, and again, coming back to Alvin's question, what the add is doing here is just executing the command but not printing the command on the screen. So you will see only the result of the echo command but not the echo command itself. Okay. So this is a very simple way to document your Makefile. We encourage to do this, but of course there are more elegant ways to do this. So and of course, how you will execute this, you do make help, and then this is going to be displayed on the screen, and which options you will have available for you to use in that Makefile. So it's a very well idea, or a really good idea actually, to document your Makefiles for your future self and for other users or other colleagues you want to share the Makefile with. Now, this is a little bit more interesting, more elegant way of documenting the Makefiles. So this represents a little bit of the structure of the rule of this Makefile. And the only thing is, I'm basically describing here the rules: debug, build, install, and the funny clean rule and the funny help rule. Now, what I'm also doing here is including comments, right? I'm also commenting, which is also strongly recommended, my Makefile. I'm commenting now. Notice that the official symbol or the needed symbol for commenting Makefiles is just the hashtag or the number sign. I'm putting 2 now. I'm putting 2 hashtags here, okay? And you will see why. This is on purpose, again, no typo here. So I'm saying, okay, it's the same comments that you saw before for the help, but now these are comments in the Makefile itself. And now my help rule, what it looks like is it says, okay, the help depends on the Makefile. Makes sense, I guess. The help of the Makefile depends on having the Makefile. But then my execution of the help rule contains the set command. The set command is a super powerful command in the Linux shell. Is like in the same category of power, I would say, as awk or sheawk or any of those. It's basically flow editor, if you wish, that can allow you to do manipulation of strings, and it's super powerful. It can be cryptic, the notation sometimes, but it's super powerful. You can even look for one-liner set commands, and you will be, I hope you will be amazed by what it can do. But I tell you what this line is doing. So this line, what it's doing is taking the Makefile. Remember, this is our symbol for representing whatever is the dependency, in this case the Makefile. So it's taking the Makefile, and then it's going through the Makefile and looking. So it's searching. S stands for search. Then the slash, if you are familiar with PI, is a similar way to specify what I'm going to be searching for. And then the hash represents whatever starts or begins with hashtag. So this set command is going to go through the Makefile itself, and it's going to search for the lines that contains 2 hashtags at the beginning of it. And then it's going to print them. So what it's kind of a hack if you wish, but it's a very elegant way to document your code, and also at the same time that you're documenting your code, generating a self or commenting your code, and at the same time documenting your code, generating self-documented help for the user. So when I run, for instance, make help, then I basically get all these options, because what it's doing is just printing each of the lines. And by the way, by putting the by putting the dash n, I believe you remove the pattern that you are searching for. So you basically just print the line without needing to repeat the hashtag, which it wouldn't be so bad, but it looks a little bit cleaner. So again, this I think is a very nice idea, especially for documenting and commenting your codes, in particular the Makefile in this case. Sometimes the division between commenting and documentation is not so clear, and it's a very thin line that separates one from the other. Basically, the comments are for whoever is looking at the script or the program and have an idea of how things were implemented or done. The documentation, on the other hand, is information for the person who wants to use the program without necessarily needing to know all the tiny nifty details that go into the implementation itself. So how you will use it, what options I have for running the Makefile, what options I have for running the program, those kind of things. So any questions about this? And again, I think this was a good idea to cover, especially thinking about what is going to come immediately after and what you're going to see in the source code for the assignment. Okay, so if there are no questions about this, let me share the other set of slides. And again, I'm going to be, for whatever reason, Zoom likes to move my chat window. All right. So we were talking just a minute ago about documentation. So, and one thing that I think Rancis mentioned last time when he was talking about modularity is that it's always a good idea, and we are going to encourage and also require that your codes have comments. Okay, that's kind of the first layer of documentation, if you wish. And actually, talking about documentation, there are many different styles and philosophies. Like some people may say, and I have heard this so many times, no documentation is needed, the documentation is the code itself. Yes, no, that won't work. Sorry. I can guarantee you, whenever you go back to your code, you scratch your head for more than 5 minutes saying, okay, what was I trying to do here? And why they did it in this way and not in another way? That has happened to all of us. And it's a very selfish attitude, if you ask me, right? It's a code, especially if you want to share your code with someone else other than yourself. It's something that is not considered best practices, and it's not helpful for anyone. So instead, we can use a strategy similar to what we did in our Makefile. Of course, in our Makefile, I told you, the last Makefile we saw, it was a little bit of a hack. So definitely there are better ways to do that. And one of the ways is to use tools that are already defined and created for doing this kind of things, for what is called auto-generation of documentation. And this is a very nice tool. There are things like this in R, in Python, and we are going to be seeing the ones that will work for C and Fortran. So the tool that we are going to tell you about is Doxygen. It's used to generate documentation. It's really nice because it basically look at your script, it figures out what functions you have, it figures out what are the arguments that it has, so it creates a kind of simple but unconcise description of the function, but also can add information based on decorations or additional symbols that you can add to your code. And it will look like comments within the code, but also will complement this documentation. If you are very serious about this, and if you're planning to create a code that can go into any public repository, the other thing that is usually really encouraged is to have a README file. something like, we ask you something like this for assignment 1 is how you compile your code and how you run it. It's a very, very lean README file if you wish. Some of you were figuring that out. Usually one put way more information. Again, if this is a serious software development project, you may have even references to further readings or papers that you are using for creating your software, or even where using it. So again, it's kind of a pyramid, how much documentation you can go, but I would say skip the no comment at all. That's definitely a no-go. And try to use tools like Doxygen that will alleviate a lot on that regards. So this is an example of how you will add Doxygen comments to your script. So for instance, this is done by Rancis. So you notice these 3 slashes and then adds. So this specifies, remember, the 2 slashes were a way to include comments in C documents, in C programs, or C++ programs. But now we have one more slash and then adds keywords. So every time that you see an add something, add file, add auto, these are special keywords that Doxygen can recognize and create a record of this and associate to the function that you are, or the file that you are using. So for instance, we have here the name of the file, we have the author name, when it was done, and a brief description of what this module does. So it's a module for writing a 1D array of doubles to text and binary files. Then we have the plain code. So we are not going to go into this. These are the defensive guards or protect guards that Rancis talked last time for the header files, whatever libraries you need to include. And then this is a definition of a function. So we have void because it doesn't return anything, the function, the arguments to the function. And what we have here, notice, is a brief definition of description of the function. And then we have the name of the arguments in the function. So param stands for what arguments the function receives. So param s, n, and x. And what is the interpretation of that argument? So for instance, s is the file name. N is the number of elements in the array to write to the file. X is the pointer to the first element. So in one way, you can think about this as commenting the code, right? I'm telling in my header file what are the arguments of this function and what this function is doing. It's perfect, right? What else can we ask about? And at the same time, I can use this to document the file, to document this module, and tell the user what are the things we are expecting. These are not proper, or what I will call comments properly of the code, because it doesn't say much about how it's being implemented. We need to go into the implementation file to see that. But it's telling a high-level description of the function, what the function is expecting, what the function is returning. Similarly with the other function. Okay. So again, bear in mind this fancy or funny-looking 3 slashes for comments, and whatever is the keyword, add keyword, that comes after these declarations for Doxygen. Okay, so that is how you decorate, how you populate your source code. How we generate this documentation? Well, we use a command called Doxygen, so you need to install Doxygen. And then the way it goes is you have different ways to do this. In particular, you will generate a configuration file for Doxygen. In this case, we are going to just say project name and project. What is the project name of the module that we want to generate? And there's going to be a docs file. And then we are going to, if you want to create a README file, a README.markdown, then you can basically look at how it will look like this. So this is a way to generate a very generic way of defining a markdown file. And these are the commands that we are doing here. Now, the other thing, and this is where it ties with your Makefile, is we can create latex documentation based on the Doxygen output. So after running Doxygen, we can say, okay, you know what, take the Doxygen output and generate latex from that. Of course, this requires to have Doxygen and latex installed, obviously. You can also generate the HTML. You can even use Pandoc. It's a very popular one, and Rancis is a very fond of it. And that's basically, so there's not much you have to do other than installing Doxygen and latex. And of course, these are already installed for you on the cluster, so you don't need to worry about that. So just for finishing this, let me show you how it looks like. So if we look at the output array function, So the HTML version of the documentation will look pretty much like this. So output arrays, a module for writing 1D arrays. So all the documents that, all the comments that you put there will be there. The write binary function will look like, okay, it's telling you the arguments, it's telling you what the function is, and it's telling you the parameters, similarly with the write text function. So again, it's a very nice way to document and generate kind of professional looking documentation for your functions. Again, any serious big project use this kind of tools. I think that's all what I have for you guys about this. Ramses is going to show you more details about this in the ANS code. Any questions so far? Let me revert this and ask you, have you guys used any kind of tool like this, Doxygen or docstrings in Python? I know we have some Python users. Feel free to answer in the chat. We just don't want to waste everyone's time. So if you have seen this before, maybe there's no need to go into much details. Okay, sounds good then. Great. It's a very nice tool to use. I strongly recommend. Cool. All right, Francis, you want to?
Yeah. So I think my little segment here is going to be just to present the code. Let me say, it's a monolithic code. It can be read, and you can probably figure it out. But let's go through it anyway, just to point out a few things, because it's not. Yes, the exercise is partly in understanding the code, but really we want you to be able to go and modularize the code. So that's the point of it. Let me go and share my screen. Which one is it? I think it's this one. Okay. Can you see the screen?
Yes.
Okay, good. So let's get into the teach cluster. So that's where we're expecting you to work. And I'm SSHing in, and there is some optional functionality in this set of code to use graphics or to produce plots, and for those to be visible on my end, so not to try and pop up somewhere on in the SciNet data center where you would not see them anyway, and where there are no screens, so it doesn't work. The -y will forward a graphics server from your local machine to the cluster. Now that has to be an X server. So on Linux, that's pretty much what you almost always have. If you're on a Mac, you might want to install X Quartz, I believe. And on a Windows machine, if you're using MobaXterm, you also have this graphics server to be ready to be forwarded already. So
sorry, Ramses, if you're on a Mac, what do I need to install?
X Quartz.
X.
Yeah,
I type it on the chat. It's
okay, perfect.
Yeah, there we go.
You probably have it.
You might have it already. It depends a little bit on the versions. Anyway, so I'm in, and you might already have a directory for your stuff for this course, but I'm just creating one. And we said that all of the files for this assignment are in SciNet course PHY1610 hands-on table. So I want to copy all of those here. And that doesn't work because it's a directory, and the directory can't just be copied. So you have to say -r for recursively go in the directory and then copy everything. So copy -r, the source, and the destination is this dot, which is the current directory, right, in Linux. So there we go. Wait, did it happen? Yes, it happened because it didn't say it didn't happen. So there it is, hands-on table. So it just has a couple of files. I put the zip file there too, but you don't really need the zip file. I'm going to remove that on my end. So that's all you have. And it has, as you see, a README. So whenever you have a code that has more than one file, you really should have a README file to say what all those things are. So we can look at it. And it says some cryptic stuff at the beginning, but then it says this is the code for assignment 2. It performs a simulation of ants walking on a table. So it does that. So the table is divided into squares. A number of ants is initially put on the table and then divided as evenly possible over the squares. So it's basically like a checkers board, but turns out it's 70 by 70, so it's a bit of a big checkers board. Less is more. So there, in Linux, there are basically 3 ways to show a file. You can do cat, which really just dumps it to the screen. It stands for concatenate, but in this case, it just concatenates one. That goes too fast. There's more, which waits for every page. And there's less, which waits for every page, but also lets you go back. And some systems only have less, they don't have more. So that's what this is, that's all. So less. And okay, where were we? Okay, so we have a table, there's ants on it, and those ants can randomly move to neighboring squares, but if they reach the end of the table, they fall off. So we'll get less and less ants. That's a good thing. And then that's what the simulation is. So each time step, a random number of ants goes in random directions, and that's what it's supposed to do. The code and then it produces some output. So it prints things to screen, mainly just the number of ants that are still left. And then it also prints out a file with, for every square, how many ants are on that square, and that for every time step. So it also tells this Makefile, sorry, the README file also tells you how to compile it. It says do source teach setup and make ants on table. If you want to generate the documentation, do make doc. If you want to know more, it's make help. So this Makefile that comes with it is actually fairly versatile. So we can look at that Makefile, and it is also documented, but it's kind of long. So let's first try and make things. Okay, so the first thing to do is to try and make, and it doesn't work. Read these error messages carefully. It says G++ command not found, and that's because we didn't read the README properly. It says something else than what we're doing. It says first do source setup. So we're going to type source setup as a teach setup. What that does is just load some modules. So these are the modules that are loaded by this. The file itself, teach setup, is pretty small. Really just a module load, GCC, and a whole bunch of modules that you might, if you did it on your own machine, you probably have the G++ compiler already. To do the documentation and produce the PDF, you need to have LaTeX. But on the teach cluster, that's not standard, so that's in a module. To use Doxygen, you need a module. And then if you want to do the plotting routines, you need either GNU-plot or Python. But as I already mentioned, those are really sort of optional. But now I have loaded these modules, and module list will show that they are there. So modules are very specific for clusters. They almost always use a module system. On your own machine, you probably don't have that, and you just install them in any old way. The point is that you can decide on your own machine what versions of what software you want and uninstall and install them. We have to deal with users that want different versions at the same time, and that's why there's modules to load those in and out. So that's what we've done. So we'll have GCC 7, we'll have GNU-plot 5, like different versions here, but the defaults are fine. Now we should be able to do make, or maybe even make the executable. So it compiles first into an object file. Remember, we were talking object files, and then it links that object file into an application called ants on table. So that is now runnable. So we can do dash ants on table, and it will run. But that's 10,000 time steps, which is bearable on a demonstration level. It will have created some extra files, ants.txt in particular, and I think that's it. So we can look at the Makefile to see how it did that. It showed us the commands, right? So that is nice. So let's open it in Nano, then we'll get syntax highlighting. It's nicer. Okay, there we go. So just as code gets documented and commented, so should your Makefile. So it has some comments to say what it's for. And then typically you start with some variables that control like what compiler you're using, so G++, and what flags you want. And there's fairly well established conventions for how these what these variables should be named. So I'm sticking to those. Even if we aren't using these particular ones, I just put them in here so you know that those are common names. But for us, the fact that we're doing C++14 is important. The -O, this is a capital O, not a 0, means we're optimizing the code. Or really, we're not optimizing the code. We're allowing the compiler to optimize things. And the -M arch equals native tells us that it can optimize specifically for this machine. We haven't gone into this yet, but compilers tend to be conservative in what they compile into. So they will try to compile to an application that you could then copy to another similar machine, and it would run there, which sounds fantastic if you're actually in the business of distributing software and you don't want to give them the source. But if you want to get the last bit of performance out of a machine, you don't want to compile for a generic version of the machines of the CPUs, but for the very specific one, so you can use all of the tricks that are available for your machine. So that's the MRG. These are good defaults to use if you don't have any reason to diverge. We've set 14 as the standard for this. Now, of course, we have to use these variables somewhere, so we'll see how that works. There's some targets here. There's an all target, which builds two things: hands-on table, which we just did, and the documentation. We haven't done that yet. How is end-stable built? Well, for end-stable, I need the object file. And if I don't have the object file, then I have to do this line. So I'm using all of the variables here, CXX. This should really be, oh wait, this is the linking stage. So these are LD flags and LD libs. We'll see use cases of those, but in essence, we're just compiling whatever went into something that goes out. So here are those special variables again that Marcelo talked about. Here's the compilation of the object file. Very similar. The CXX flags are put in place here so that they are used. If you leave them out, it's not automatically used. So be a little careful. Then there's apparently also a run rule. That's great. So we can actually type make run and clean and this clean were things that were explained as well. And then we have this help. So this can be useful, and I do like this idea to have a make help, because if let me exit this for a second. If I type make help, it's not very nicely formatted, but it tells me all the rules and what they do. But it's fake. Like it doesn't work automatically. Like if I do just help, it actually tells me how make can be used, but not what the Makefile can be used. It's fake in the sense that I made this happen. Let me go to the curly braces in a second. So I made this happen because there is a help. Oops, my fingers are used to Emacs help. What it does, it actually looks at all of the Makefiles and picks out all of the lines that start with 2 pound signs. This is a set command that uses regular expressions, and you don't really have to understand it to use it. But that's what it's doing here. It really just goes and picks out all of these lines that start with 2 pound signs. So I have used that, and everywhere when I wanted a rule to be documented, I use 2 pound signs. So it's kind of self designed, right? This is not automatic. Just because you have 2 pound signs doesn't mean that it will pop up in help. It is because the help rule scans my Makefile for those and then prints that out. So it's slightly different than in the slides, but it does exactly the same thing. Okay. Then I also have rules for plotting and documentation, and I put them in a separate file, which we can include. So separate Makefiles, just to keep things self-contained. So even Makefiles can be modular, right? So the main part is really this part, right? It's the linking and the compiling. The running are nice, and then the documentation is done in the documentation part. And you don't really have to know how it's done, but we can look in the code and some table.cpp to see that it is filled with Doxygen style comments. So every function has these triple slashes and params and all of that. And so when we do make doc, it actually creates a Doxygen file that contains all of the configurations. That's highly customizable. So the default will not look very nice per se, but it will work. And then it has created this PDF for me. It also has created a PDF. It also created a directory called HTML, which is basically a website, but it's not public. So it's really just a bunch of files. And on the Teach cluster, we don't have a browser, so you can't really open this website, although the website looks a little nicer. But I can open the PDF. So let me do that. Oh, there's a question why I had, let me just go back to the Makefile, why I had curly braces and round braces here. That's just me being inconsistent. As far as make is concerned, both are valid as long as you use a curly on the left and the right, or a non-curly on the left and right, it's fine. And RM is predefined in Make. Really, I should have said something like RM equals RM minus F if I wanted to be explicit, but it turns out that Make has a few things in place just by default, and this is one of them. Okay, so there's a question. For modularizing functions, some functions like the single step of a for loop require lots of variables defined outside of a scope. Yes, that could well be. So let's look at the we're going to go into the source code in a second. Let me just show you what the documentation did for us by putting in those files. Those Doxygen commands, so we can see it in action on a PDF. That should work. And I have to share that instead of the original. So stop share screen, and some table. There we go. So now we have a PDF. The PDF doesn't look very nice, but it does have all of our information in it. So there's a table of content. We don't have any classes, you would think, but there's actually a struct which counts as a class, so direction. So there's a whole chapter for, hold on. So there's a first chapter that has the main page. The main page is taken from the readme.md, which is nice. So you have your readme, but it also gets put in here. We just read the readme already, so that's fine. And that is actually really why, if you remember, the readme had that first funny line. We'll look at it later if you want, but it had that first funny line that really basically forces Doxygen to put it into your documentation rather than just leave it out altogether and say, I don't know what this file is. So there's a list of classes, which really has just one struct in it. There's a file index, which now has one file. So this seems like a hopelessly over modularized version of our code because it's one file, but it won't remain that way. So we will have a file list of all of the files at some point. And then there's class documentation, which is this one struct. We'll look at it in a second. And files. And the file documentation will also contain all of the function documentation. So there's 4 functions in this file. They're called linear, rand, partition, write array, and main. It's all hyperlinked. So if I want to know the linear function, I can click on it, and it goes to the linear function. It tells me what the parameters are. So all of the information that is in those Doxygen comments has been put in here in a relatively self-contained form. without me having to write this document. That's good. Okay. Okay, so let's look at the code then quickly. So this one, I think it's this one. Yep. And let's do that in nano too. .cpp. And it's just wide enough. Okay, so we start off having some libraries. We're going to do IO. We're going to write to a file, and we're going to use this random library, which we'll look at a couple of weeks from now to see how you use random numbers in C++. There's a standard library called random, which is very decent, and you should use it unless you have a reason not to. And we're using it here. These ants are going to go in random directions, so we'll need that somewhere. Okay, so what do we have? We have a struct. A struct is a combination of different variables. In this case, I have two integers, a di and a dj. So every direction contains two components, and these are shifts. So the ants are going to shift. They're really going to shift either one left or one right or one up or one down or any combinations. So those combinations are going to be stored in directions. So we're going to have 9 possible moves. Staying on the spot is also a move, and the 9 possible moves are just put in a constant array called moves. There's 9 elements of that. Each element of the array is a direction, and I just specified what they are. So you either go left and up, or left and stay, or left and down, etc. There's probably ways to do this programmatically, but since it's just 9 moves, this is pretty easy to just put in place like that. Okay. So that's for every ant a possible move. Then there's a linear function. Now, this is a monolithic code, and it doesn't have any prototype. So all the functions are used later that only make sense when they are used are already defined here. This is one of the other reasons why you might want a more modular approach. But it does explain what it does. It computes a linear index for a matrix in a 1D array. So let me just, there really should be more explanation here, which I can't because this is the brief one, but I can do more. It doesn't matter. And I can say this is necessary. Okay, I can't write anymore. It's necessary because we're using 1D array. So there'll be a 1D array, but this is a table, so it's a 2D something. So what happens is every row in one, every row is stored, and then we have one big array that stores one row, and then right after that, the next row and the next row. So we basically cut the table in slices and paste them all together. That is how we're going to store how many ants there are on each spot. Now we will want to know, because we have to know what's up and down, what actually, given a specific position on the table, what is its position in this linear version of the table? And so that's what linear does. It takes a row index and a column index. So we imagine this table to be rows and columns, and we'll give an index. It starts at 0, like everything in C++. So row 0, column 0 should be the first element in this linearized table, right? And so this is just a way to encapsulate that computation of what the linear index is in the linear array versus what the real index is in the 2D table that we have in mind, or in the matrix if you want. Okay, so that's just a function. It's going to be everywhere because we're using this linearized stuff. We will later see better ways to do multidimensional arrays, but we're not there yet. So this is one way to do it, but we will need to be consistent in how we map 2D coordinates to a 1D index. That's what this does. It turns out we don't really need the opposite. You could imagine having to have an opposite too, where you give the linear index and then what's the row and the column. It turns out in this code we don't need it, but that's it. Okay, so that's going to be used. There's another function that does something completely different. It's called rand partition. You'll notice that I don't put the name of the function in the description because it's right there. So that is, you could do it. It's not a huge mistake, but when you have your documentation auto-generated and it says void rand partition, the function void rand partition does this and this, it's kind of duplicate. So people don't like to do that. So it's a function. What does it do? It takes a number is called total. You can see it's one of the inputs. You can also see it here. It's one of the inputs. And that's a number of ants, and it subdivides that number into 9 sets, or really in n parts sets, and it does it randomly. So suppose I had 10 ants, or a number of 10, and I asked it to randomly divide it in 3 parts. I could get 3, 3, and 4. Or I could get 5, 4, and 1. Or I could get 0, 0, and 10 randomly. And it uses the random number generator. So that's going to get used in a way where we know how many number of ants there are on a certain square. They can all go in one of 9 directions. So what we do is we just split up that number of ants into 9 groups. And then the first group goes left, the second group goes up, etc. Right? Rather than having to decide for each ant separately where they're going, we just subdivide the group into 9 groups and send them off their merry way, which is way more efficient than doing it ant by ant, at least if you have a lot of ants. If you hadn't guessed, a couple of years ago, I had an ant infestation in my house, and so that's when I wrote this code. It's part of my frustration. Okay, so it's a function. One thing you should notice, and what you should try, is that every function should not use any global variables, right? So everything is defined either inside of the function or is passed into it. So there was a question: if you need a lot of variables that are defined somewhere else, do I need to pass them into the function? And the answer is yes. If you need a lot of variables, you might want to think of, do I need them maybe to be defined inside of the function? So here's a function like random partition that needs this engine thing, but it also needs another variable called uniform. And while we don't have to understand what this does exactly, I could have defined uniform somewhere outside of the function and just use it or pass it in, but I only need it here, so then I can define it inside the function. So keep in mind that that it might be possible for a variable that's only used in, say, the time step function to be defined in the function that does the time step. Right, so that we're not going to go into why this works. You could read it. You might be able to understand. It's not terribly difficult how it does it, but it uses a library that we'll look at it later anyway. So let's not waste time on that. Okay, now next function. Kind of random because we haven't properly modularized this, but we're going to need a function to write the matrix to a file. And in fact, we're going to write it to an open file stream. So we're going to have a file stream that should already be open, that's going to be passed in, that we're going to write to. We'll have an array. The array will be an array of integers. The number of ants are integers. It's going to be one linear array. So that's where that linear stuff comes in. And we'll have to pass in the number of rows and number of columns. As I explained in the C++ part, if you pass an array to a function, a standard C++ array, it's going to be just a pointer. Even if I wrote this as if it was an array, the function does not get told how big that array is. So might as well not pretend like it's an array. And so I have to say how many rows and columns there are. That defines the size of the array. And what it does is it just goes over all rows and all columns and writes out the integer that is there. But because it's a linearized array, that's where it does the translation from ij, that is the 2D coordinates, to a linear coordinate inside this sort of linearized, pasted together rows representation of the table. There's a bit of an odd indentation here. Might depend on your editor how this happened, but it's supposed to look more like that. Okay, and then finally we have our int main. Is it common to use linearized arrays? Yes and no. And all arrays under the hood are best performing if they are laid out as if they are linearized. So we call that contiguous in memory. But the way you work with them, you really do not want to have to think about calling a function. In fact, you could time this, but it turns out that calling the function itself has some cost, and so that's not great. And sometimes the compiler can do something about it, and sometimes it can't optimize that away. So we'll see that there are better ways to do this, but the C++ standard really doesn't give you a very good way to do this while maintaining a contiguous memory. There are these still things called std vectors that we talked about, which you can nest, so you can make vectors of vectors of vectors, but they're not actually contiguous. So that destroys at least that part of your performance. So we want to be able to keep the performance, even if right now it's not that important yet. And so we'll have a whole lecture spent on that. That's one of the reasons why. So linearized arrays aren't uncommon. There was a time where that was always how you did it, and it wasn't very expensive to do it, so it was a good way. Now it just sort of gets in the way of reading the data. Like, I would love to have this be Aij, and just be done with it, right? And have the rest just be nothing. That I get that much better. So it's not very common, but it does happen. Okay, so the main function. This is the real meat of the thing, right? We're defining some parameters. The length of the table is going to be 70, so it's going to be 70 by 70 squares. We're going to take 10,000 time steps. We'll put in 40,000 ands initially. We'll put in a random seed. So when we're talking about random numbers, we will find that to control which sequence of random numbers we get, we can set a seed, which basically sort of tells it where to start. Not the number it starts to, but how to start it. So it's kind of like its fuel. And by setting it a specific value, we can make sure we get the same set of random numbers. If that sounds counterintuitive, just wait until we actually discuss random numbers, but that's what it does. If I change this, I get a different outcome. If I keep it the same, I get the same outcome, but it is still random in some sense. Where do we want to write to? We want to write to a file called ans.txt, so it's a text file. And just because I'm opening the file here right away, so the offstream is generated here. When we're talking more about I/O, we'll see that it's a good idea to open your file once and write to it and close it at the end of your application, just for performance, rather than to open and close it all the time. So we're opening it here once, and then we'll use this file. Ans file is what it's called. Then there's some arrays that we need. We need an array for the number of ants. This is going to be one long line. How many elements do we need? We need length times length element. So that's this linearized array, if you want, a linearized table. Turns out the way that the algorithm works, we're going to take that table and then create a new table in which we are going to put the updated number of ants. So we have old number of ants per square, and then new number of ants per square in a different array. So it's called new. So we've got it here. We're going to have to partition every square off into 9 groups. So that's what this is for. This is just to contain those groups. And then we're also going to keep track of the square with the smallest number of ants and with the largest number of ants. And that's just so we kind of can keep track without having to visualize the whole table on how it's going with our simulation. So it's going to output these things. So those are some arrays. Some of these you will notice can actually be put in later and can be modularized, but that is your task. We need something to produce random numbers. That's called a random number engine, and that's what this does. And as I said again, we're going to look at random numbers later, so you can sort of trust that this works the way it's supposed to. You need this engine, and it needs to be initialized, and this is a good spot for it. Then we're going to initially put all the ants evenly on a table. Again, this is a trick in a sense that you don't entirely have to understand at this stage why it works, but it does work. It computes on the basis of the linear index in the table how many ants should be there. This is a long a long formula, but it does work. So that's all we really need. Then it counts the ants. This is actually a good check to make sure we actually put 40,000 ants on it. So it starts computing the total number of ants here by looping over the table. And since everything is stored linearly, we have to keep computing this n, the actual index in the linearized array, which, as I promised, we will eventually get rid of. And then it computes the minimum or the maximum of the number of ants. That's it. Now the ants are there. Now we can start our time steps. But we do want to write to the simulation, to the text file. And before the simulation starts, I want the initial condition to be in there. So one part goes to the screen, cout, one part goes to the file, ants file. And because it's just a function, all I'm passing here is the open file, the number of ants, which is this array, right? And then the size of the array, which is length by length. I don't have to know anything else here to write to this file. Then the time steps. So this is a simple loop. Number of time steps was set above. And here's where we're going to create a new table. The table's already created in terms of memory layout, but it has to be initialized to 0. So so this new table has 0 ants on it, and then we're going to move the ants into this new table just based on where they go. So we go over the whole table. So that's this double loop over I and j. N tells me actually where in the linearized version of the table I am. And then we're going to check first. It doesn't make any sense to move ants if there's no ants on this particular square. So if the ants is larger than 0, then we'll do something. And what we'll do is we'll use this random partition thing to partition this number of ants into 9 different numbers. And each of the number will go in different directions. So the n moves will contain the number of ants to go in each direction. Then we go over those moves, and we figure out, based on our current location, I, and the direction that particular move goes into, the di dj. So that's that old moves array from up top. This tells me where the new location is of this set of ants, and I'm going to put them there, unless they fall off the table. So this could give you, for instance, an I2 that is less than 0, which means it's off the table, or bigger than length, which means it's off the table. So I'm only going to put it on the new table if it hasn't reached the edge. And so if it hasn't, that's what this if statement does, then I'm going to see where in the new table this fits, and I'm going to put my ants there. Okay, so just the ants that went in that particular direction. Now this is in the new ants. Now I have to update to make the new equal to the old, or make the old updated with the new. So that's another loop, and just as number of ants equal to new number of ants. Now that that's updated, I can redo this computation of minimum and maximum. So min, max, go over the array, and that gets printed out, and oops, and written to a file. This is the closing brace of the for loop, so of the time steps. And then I close the file and return 0 just for good form, although I mentioned it's not really necessary here in main. And that's it. That's the computation. So let's see what it did. We don't really need to save anything. It's fine. There's nothing to be made, but I can run it. I can do make run. There we go. And that would have created this ants.txt. And then there's a Makefile for plots. What was it called? Plotting.make that uses either GNU-plot or Python. I don't care which one you prefer. The GNU-plot pops up on screen, so I'm going to do that one. So I'm going to do make plots. Turns out to be a shortcut for make, plotting, and then I think it's plot. Let's see. Okay, now you're not seeing this because I have to stop sharing and share the other parts. So share the screen. Where are you? That's not it. That's not it. This is strange. What happened? Maybe I was too soon. Share the screen. I don't know why that doesn't pop up. Screen one more time. Okay, does this one show up? That's strange. If this is visible. And try making the snapshots PNG instead. That works. In any case, the plotting can be especially useful if you're modifying the code and you want to make sure that it is still working. Those numbers that fly by on the screen when you just run the application might not be so clear. Thanks.
So that's what I get, Ramses.
So it made 4 snapshots for different times. You can see it's fairly uniform initially. That was exactly the point. They're all 8 or 9 of all 70 by 70. And then it should not surprise you that there's less ants on the edge because that's where they fall off. So it's less and less. And as time progresses in a random fashion, you get less and less ants.
Okay, Ramses, thank you. That was very good. We took the whole hour, but maybe if you guys have any questions, can quickly go through it. It's in the chat.
Syntax. Rob, do you have a temp account?
Yes, I do.
Okay, so in the temp accounts, so in the 516, there should be a file called .nanorc in there that basically does all of that. So if you want the same thing on your own local machine, there's these includes at the end. Okay. If you're on your own Signet account and you don't have that, feel free to copy it from mine. I think it's publicly available, so you can copy ~arson, that is my home directory, nanorc to your own home directory, and that would work. I don't mind. It's fairly generic.
Okay, no, I think that would be quite useful.
Yeah, I like Nano can do it, but it doesn't do it by default for some reason. but I do like it. It helps me out. Let's see.
Question. So how to export PNG or PDF file from Signet to the local computer? If you mean like visualizing, for PNG you can use display PNG as a command, or for PDF, as Francis showed earlier, you can use XPDF. Those two commands should be in the teach cluster, I believe.
Yes, display and XP. You have to have SSH-Y or -X for that to work when you logged in. So when I logged in, I did -Y. Depends a little bit. -Y tends to be more stable. Other than that, there's other differences.
In some Mac OS versions, -Y is the only one that works.
So, if you want to copy it over, it's like any file. So you can do an scopy.
We are not seeing your terminal.
Oh, sorry. Let me share.
Yeah, I was going to ask if you can put the command to enable syntax highlighting in Nano. In the
Oh
chat
yes,
box.
that's why I didn't make as much sense.
Sorry.
I'm showing you. No, I'm not. Okay. Sorry about that. So once more to SSH in teach.
Notice the -Y that Francis is putting there. That is what allows to have graphics forward into your terminal.
Then and some table. Then things like XPDF and some table.pdf would work. I'm only sharing this one window so that you're not seeing that, but it does pop up. If it doesn't, you might have might get things like messages like cannot open display. That means most likely that you either forgot the -Y or you didn't have an X server on your local machine. And we could help you fix that, but that's the most common thing that can go wrong. The Nano thing is in home directory nano rc. So here it is, and towards the bottom of that file, there's lots of options. There are these include files, and these are just standard include files. That's why they come from standard locations. But by doing that, whenever I load a .cpp file, it goes and uses the C syntax, and Makefiles have their own syntax. And so there's quite a few supported. I just include them all because I don't know what I'm going to be opening. But there's a slight performance issue, but I've never really seen that on any modern machine to be an issue.
So for Michael's question, yes, that's the main task, is to modularize this monolithic code. Yes. So basically take your functions, move them away. You need to create a function for the main part of the time step. Just to be clear, the main for loop remains in the main code, but then whatever is inside should be modularized. Yeah. And with modularized, we mean having header and implementation files, as well as Francis mentioned earlier, proper variables coming into the functions whenever it's needed, right? Okay, so again, we took way too much time, or a little longer than expected. But I think it was a good inversion of time going through the code to explain what was going on. If you guys don't have any further questions, we will stop here. We're going to post the recording of this in two chunks. The first part where we finish the material for Make and the documentation, and the second part probably on the assignment website with the explanation of the code. And if you guys have questions, you're more than welcome to use the forum or email us. So